Hi everyone, this is David Greenberg from Helmholtz from Hereon. We are coming to you with episode 34 of our machine learning seminar. We have a really interesting paper on spectral bin representations of cloud microphysics presented by Shivani Sharma, our PhD student. The idea to look at this paper came actually from last session when we had a really great presentation by Matthew Chantry. One of Chantry's notions that he advanced was that it's sort of easier in some cases to learn stable, accurate parameterizations with machine learning for expensive processes which already exist in climate models and weather models than for processes which are typically not included but we want to do better. This current case is sort of an intermediate middle ground. It can and has been coupled to running climate and weather models, as we'll see, but we're not just trying to make things faster. We are really trying to make things better compared to the normal operating procedures of these models. And the cloud processes, which we'll be investigating, as the paper notes, are really important for predictions of rain, but also for longer-term climatic predictions, because they're very important for radiation balance. So with that, I will turn over to Shivani.
Yeah, thanks. So David already introduced the basic premise of the paper, but before we get into the paper, I think it would be a good idea to first have a bit of an overview of the different cloud microphysics schemes that there are, and then sort of describe the problem that they are trying to solve. It's usually used as a nice test case for different microphysics parameterization schemes, and then we discuss the model setup, the results, and the conclusions. So just to quickly go over the way the cloud microphysics parameterization schemes are designed. So clouds exist in varying scales, and they can be quite hard to model because of that. And the parameterizations that are used try in some way or the other to approximate these various processes and the interactions between different hydrometeors involved. But even so, clouds remain a big source of uncertainty in climate models. And the primary issue actually arises from the challenges in representing these processes that are approximated. And also recently, with the prevalence of convection permitting kilometer scale models, cloud microphysics has become even more important in the models and has kind of become the main driver for all the processes that ultimately lead to any sort of precipitation. So the main problem here is the accuracy and speed trade-off in the parameterization schemes. So if you see on the left, the schemes that are most widely used, the bulk moment schemes at the very bottom, they can be run much faster, but they are low on accuracy in terms of how realistic they are. And as you go up the scale, you get more and more accurate schemes, the bin physics schemes, and then the droplet based schemes at the very top. And bulk moment schemes, which are the most widely used, they usually are derived from empirical formulas. And these formulas are in turn derived from experiments, usually in a large eddy simulation model. And they basically calculate different process rates, and depending on those process rates, evaluate the changes in mass and number concentration of the hydrometeors. As we'll discuss later when we discuss the basic problem premise here, that in this case, it's only just cloud droplets and rain droplets. And these bulk moment schemes, even though they are faster and are the most widely used in operational models, it can be quite tricky to represent ice and Groppel, mostly because of the different processes that are involved in order to see the evolution of all of these hydrometeors. The most accurate ones well, I shouldn't say most accurate per se, but more realistic ones, the particle-based schemes at the very top here. They were discussed in episode 22 by Axel Seifert when he presented his work, and they usually have a sort of approach where they have representative particles called super droplets, and they follow a Lagrangian approach to see how things change. But in this paper, they are focusing on these intermediate schemes. These are called bin based schemes in the sense that instead of just calculating, unlike the bulk moments where you calculate only the mass and the number concentrations, you actually look at the whole distribution. So the original droplet schemes actually had around 60 bins within them, and they evaluated the evolution of the particle size distribution in time. But the particular bin based scheme that's being targeted in this paper, the Tel Aviv University bin microphysics scheme, is a slight modification of that approach. Instead of 60, it has 35 bins. And also at every point in time, when after seeing the evolution of the particle size distribution, they also calculate, just like the bulk schemes, they also calculate the mass and the number concentrations for each individual bin. So you will have 35 multiplied by two numbers, yeah, 70. And this is done to because the problem with bin schemes sometimes was that this approach of just looking at the particle size distribution sometimes led to anomalous droplet growth, and using kind of constraining the mass and ensuring mass balance prevents this from happening. And we'll go over a bit more in detail how this is exactly used in this study. So the warm rain scenario that they are trying to model, it's a very simple, well, simple in terms of the interactions involved. It's a test case that's usually used for almost all microphysics schemes. So in this case, you only have clouds and rain, and only two process rates. So one of them is auto conversion, which is the rate of which the rate at which the clouds are changing to rain because of increase in their size, and it's kind of an artificial process because in this case you decide which droplet size you choose as the threshold, and based on the Kessler scheme on which the modern bulk moment schemes are usually derived, they have a fixed particle size, and all the droplets below that size are considered clouds, and all the droplets above that size are considered rain. The other process is accretion, which is which is the process through which the rain droplets, the cloud droplets accumulate over rain droplets. So as you can imagine, at the very beginning of the process, auto conversion would be the main driver, whereas later on, as there are more and more rain droplets, you can see more accretion happening. So these are the two processes on which this whole warm rain scenario is based. So this is something directly from the paper. So they have two main objectives in this paper, and they are trying to test them. So one of them is that in a global circulation model, what happens if you change the inherent microphysics scheme? So they compare running the global circulation model, in this case CAM, in a scenario in which it has a traditional bulk moment scheme, and the other one in which they run it on the tau bin scheme. And secondly, they want to see if a machine learning network can indeed learn this bin-based scheme. So the reason for that is they realize that when they use a bin-based scheme, the model slowdowns by 400%. So the reason for using machine learning here is that it would enable them to use a more accurate scheme, but in a faster way. And then they also run a lot of tests to see if the machine learning network, the machine learning emulator, is able to reproduce the behavior of the bin-based scheme in a coupled mode. That is when it's run within a model. So just to quickly go over the data generation pipeline. So when they run the GCM, in this case CAM6, with these bulk moment scheme, they usually refer to it as the control simulations, or also alternatively as MG2, MG2 being the bulk moment scheme that they use within this model. And the other one is when they run CAM with the tau bin microphysics method, and that is usually referred to as tau bin. And this is the simulation that is used for training the machine learning model. So they run their model at about 1 kilometer resolution with 32 vertical levels. And the data used for training is for 2 years. For evaluation, another 1 year of data. And later on, when they study the climate impacts, they run the model for 9 years. So yeah, how tau bin is applied in CAM6. So they start with an initial distribution. It is usually a gamma distribution, as it is in case of all cloud microphysics schemes. Run it through the quasi-stochastic collection equation. This is the basic sort of assumption or equation through which you simulate which drops interact with which ones and how they collide. And after that, they calculate the mass and the number count for each bin. And through the calculating the differences with the previous time step, they get the tendencies. So this is actually the only difference in calculation of tendencies here, because as you can see here with the bulk moment schemes as well, all they need is tendencies. So just the way of calculating those tendencies has been changed, modified. And another interesting thing is how they threshold the rain and cloud droplets. So I think I mentioned that in bulk moment schemes, they usually have a fixed number. But here, it is dynamic. So at every time point, at the beginning at t equals to 0, you might have more clouds and less rain. So they look at the local minima of around the point where there are clouds and also rain, and take that as the threshold value. And anything above that point is considered rain. Anything below that point is considered cloud. And after a while, it might be reversed in that there might be less clouds and more rain. But the process remains the same. They still look at the local minima. And they have actually written it in the paper that there always was a local minima at this location. And it's usually between 40 and 100 micron. So that's another difference from bulk schemes here. Now, looking at their model structure. So it's quite interesting here because they haven't used just one model for calculating all the process rates. They have used a combination of different models. So they realized that when they run the GCM on tau-based tau bin method, they realized that a lot of times the tendencies were 0, and intuitively it makes sense because a lot of the times it's more likely to not rain than rain. So before they start with the regressor and to calculate the time and calculate the tendency for the next time step, what they do is they have these classifiers in place. So these classifiers actually check if the tendency in this case QR being the tendency for the change in rain mixing ratio, NC is the tendency for change in cloud number concentration. Similarly, NR for change in rain number concentration. and see if they are zero, not zero, greater than zero. And these are very intuitive. So QR, the rain number, can only increase. So if it isn't greater than zero, then they just set it to zero. Yeah, and if it's not, then they try to put it into the regressor, which is also another neural network, and evaluate. And here they also try to locally maintain the mass balance, in that the change in the gain in rain should be equal to the loss in cloud, so that the mass conservation is maintained everywhere. And all of these networks have 4 layers and 60 neurons. And if I remember correctly, they train their models for 10 epochs. Now, just looking at some direct results from this. So they, at the very top, just comparing with the emulator and the data that they trained on, they find a very good correlation between the values as would be.
I'm sorry, Shivani, can I interrupt with a quick question? I'm not quite following something.
Yeah.
So you showed this simple 4-moment bulk scheme, which is
Yeah.
the control, right? Then you showed this spectral bin scheme where you have these histograms of 30 bins or something, right?
Yeah.
But then with the neural network, it doesn't seem to be calculating an update on the histogram, but rather on some other parameters describing the shape of a distribution. Did I miss a step somewhere?
No, okay, the idea is they're not just directly looking at the histogram, but the mass and number counts are derived from this histogram. So, and hence the tendencies are just the differences with the previous time step.
I see. And the input and output of the
Yeah.
neural network is the 4 moments, the number counts and mass counts, and something else too, something to do with a slope parameter?
Yeah, all the other, I think I should mention this, all the other parameters that are going in there. So these slope parameters are equivalent to the shape parameters. As I mentioned, that you at the very beginning start with the gamma distribution, for example. So these are, so they also have these inputs that are going to be the same throughout the simulation, I suppose. Yeah. Am I clear? Or
I think so.
okay.
Yeah.
Yeah. Okay, so yeah, these are just the direct comparison results between the emulator and the data that they had, and all the tendencies, and there's a pretty good agreement here. And then here, because one of their goals was also to look at compare the two microphysics schemes as well. So as you realize that they generate very different results. They don't quite match. And we'll see, especially when they, in a coupled mode, how this turns out. Okay. They also do this for looking at the distribution of values. So the purple one here is the tau microphysics scheme. The yellow one is the bulk physics scheme, and the blue one is from the machine learning emulator. So at most points, you can see that it's usually kind of it matches pretty well with the data that it was trained on. But also, if you look at the differences here in the distribution, uh, you kind of start to realize that at the very extreme ends, at least, it underestimates the frequency of extreme values, and kind of narrows the distribution as such. So, and the effects of it are then shown later on. But here as well, you can see that the distribution using the bulk scheme is actually quite different. And these are when within a model how it works out. So this is the ratio of the process rate, in this case, the tendency for change in the mass of cloud QC, um, with respect to when it's run with when the model is run coupled with the machine learning emulator, and then when it's run coupled with just with the bin microphysics scheme. The areas that are white, they wrote in the paper, are the areas where the tendency was very, very small. They're usually in the tropics. And if you look at the zonal area, it's usually at the high altitude. So most of the time, the process rates are within plus minus 20% of what they were in bin microphysics. But there are some differences, especially in the Southern Ocean. And these again will come into play when they look at the climate. Looking at the globally averaged vertical structure for temperature and cloud, they match pretty well, all three of them. The control simulation tau and tau ML, which is the machine learning emulator. But when they look at cloud liquid path, uh, you can see here that especially around 800 hectopascal, it differs quite a lot. So the ML emulator over overestimates in comparison to the algorithm that it is trained on, but both of them are actually quite different from the control simulations. And for rain, it's also, there are some differences for rain as well, but more notably for cloud liquid path. Yeah. And these are now, they just look at two different regions here. So at the top, it's the Southern Ocean. At the bottom, it's Barbados. And they're looking at the process rates here. Um, there are a lot of process rates mentioned here. They don't actually go into the details of these within the paper. But the key thing to note here is that if you look at the differences, you see that as well, that the machine learning emulator has a lower loss of condensate around this 800 hectopascal, again around the same area, you can see that. And there aren't any significant differences when you look at Barbados. As you'll realize that the Southern Ocean region actually is the area where all of these differences seem to be more noticeable. Now, another problem that they came across was the mass conservation. So I think I mentioned that they do try to conserve mass locally, in the sense that the change in cloud is the loss of mass in cloud is reflected in the gain in mass by rain. But also, as they do some climate studies as well, running the model for 9 years, there are cases when the mass and the number counts actually turn to negative. And in order to take care of that, they actually use a hard constraint, and they adjust the tendencies when they produce negative moments. And here you can see that this is basically at the very top, and at the top they're looking at it zonally, how many times the mass fixer was activated, and below they're looking at it from a global point of view. And you can see these yellow areas are all in the Southern Ocean, which is where mostly the mass fixer was called. So this is the area where the machine learning emulator is most likely to run to a point where it is producing negative number and mass counts. Yeah. And now they go into the comparison of, I mean, they were still doing it, but more detailed comparison of just the bin microphysics scheme and MG2, which is the bulk scheme. So just looking at the process rates as well, you can realize that they're not always in agreement. And there are areas where the process rates produced by the bin microphysics scheme are more likely to be high. And then there are areas where it's the complete opposite, where the moments produced by the bulk microphysics, um, the bulk microphysics scheme are more likely to be high. And then they look at rain rate. So the bulk microphysics schemes are known for producing these kind of unrealistic rain rate scenarios where even when the effective radius is very low, it can produce but the liquid water path is high, which is around this area. The rain rate can be quite significant. In this case, the blue area, it's over 1 mm per day. But if you actually switch to a tau bin microphysics scheme, it it's a bit different, as when the effective radius is low and even when the liquid water path is quite high, the rain rate usually is very low. And this is again reflected in tau ml microphysics scheme as well, which makes sense. So this is actually, in terms of how things should be, in terms of how the physics behind this should work, more realistic. uh, there sh- um, there should not be any rain formation or high amount of rain formation when the droplets are very small in size, even though the liquid water path might have a higher value. Looking at, and then they go on to look at the general precipitation pattern. So yeah, on the left, they are comparing the frequency of they are looking at globally all the warm rain uh, uh, situations and comparing their frequency in terms of how much precipitation occurred per day. So you can see that for the control simulations and for tau ml tau and machine learning, the red one with no fixer, the differences are quite significant. And as soon as you put a fixer on the machine learning uh, emulator, um, you have the green line, which follows the blue line, which is the control simulation, much more closely. And on in the other plot on the right, the they actually compare it with CloudSat, which is a satellite. So satellite data would actually be considered the baseline, more accurate data in this case. And they look at the distribution throughout the latitude. And so, as such, the bulk microphysics within CAM is known for overestimating the frequency of precipitation. And you can see it quite clearly here, which is the line in blue. But the machine learning model and the tau bin microphysics model, they do try to kind of bring it down, but I mean, it's still not even close to how it should be. Um, yeah, this is total precipitation, and this is just precipitation over the ocean. In which case, at least around the tropics, the machine learning models are actually kind of better and more realistic and produce more realistic results than the traditionally used bulk moment scheme in this case. Now, there's a section in between where they look at some climate variables as well, some other climate variables, and but they do come into play in this section. So I'm skipping that a bit and going into something really interesting here, which is the cloud aerosol interaction. So so changes in the aerosol concentration affect cloud formation because they change the cloud condensation nuclei. And depending on the type of aerosol, this can go both ways, either way. And these remain a huge source of uncertainty, how aerosols are affecting cloud formation. And they use this quantity ACI, which is the change in net radiative effect when aerosol forcing is introduced. They use aerosol forcing starting from 1860 levels, and they are looking at the distribution throughout the latitude. You can see here the blue one being the original CAM6, and the green and the red one being tau and tau ml. They have a higher value of ACI. It's only slightly higher. By higher, it means more negative in this case. And it's especially more prominent again around the Southern Ocean. And there's a lower change in LWP. Actually, if when they average out the LWP value, it wasn't much different. And the drop number concentration remains kind of the same. So this kind of puts into perspective that changing the bin microphysics scheme actually can change a climate variable in this case. And then looking at cloud feedbacks, so here they evaluate how things would evolve at plus 4K, so plus 4 degrees. And they look at short wave cloud feedback, long wave cloud feedback, and the total. And here as well, so lower, so they realize that there's lower feedback in the Southern Ocean when they are using tau or tau ml, and lower LWP. We also saw a lower LWP around the same area. And this implies, while the ice fraction, this is from another study, remains the same. So this kind of matches with the aircraft observations over the Southern Ocean, which is that in traditional CAM6, it kind of underestimates the amount of ice clouds over the Southern Ocean. Whereas this is something that is captured by the bin-based schemes. So yeah, these are some of the climate studies that they have carried out. They ran the model for, at least for this one, for 9 years, from what I know. And yeah, so in conclusion, so the study actually shows that the ML emulator is able to learn the process rates, and even in online situations is quite stable. And it is able to kind of follow the behavior of the tau bin scheme, even in the scenarios that it hadn't seen before. The introduction of mass constraint is useful for stabilizing the model. And the change in the microphysics scheme actually leads to a very different climate. And there are cases where the little features that are produced by tau ml scheme might not be tau or tau ml scheme, actually might not be unrealistic. But when you look at things like precipitation and onset time of precipitation, it actually does better than CAM, the original bulk parameterization scheme within CAM. And the cloud radiative effects in total, when you calculate the net, actually remain similar. So it kind of, and this is a thing that the authors have also mentioned in the paper, that so does this mean that the presence of maybe, improved representation of aerosols, or improved onset time for precipitation, do these things maybe average out in the long run and might not matter when you are actually doing climate simulations? So yeah, that would be all from me on this paper, and I would be happy to take any questions now.
Thanks a lot, Shivani. Okay, nice presentation. We have a question already from the chat. Björn Lutjens, you can ask your question or I can read it. I'll go ahead and read it for now.
Yeah.
Oh, go ahead.
Yeah, I can read it. So I was just having bread in my mouth. Yeah, so you've mentioned earlier that the paper reduces the runtime by about 400 times. And I was just wondering where exactly the gain in computation costs come from, because sometimes I see a big number stated in computational runtime gain, but the comparison sometimes in the details seems to be somewhat unfair. So I wondered where that computation cost comes from and whether they did any experiment to validate the actual reduction runtime to be around 400.
So the bulk moment schemes, which are traditionally used, have 4 variables which need to be calculated, and their evolution in time, that is where the computational resources go in. And when you have a bin based scheme, and in this case they use the tau bin scheme, you have 35, actually 70 of these variables. So it's just the calculation of all of these and evaluating them in time that actually, from what I would imagine, makes it so much more slower than just calculating the bulk moments. And because the more bins you have, the more things that you have to calculate, the slower the model can become. So that's the broader concept of it, I think.
So what's computationally expensive is that we have to calculate 35 variables at every time step. And we calculate these via differential equations, or?
Yeah, I think I did not go through it. I skipped that part, which is this, the whole calculation part as such is being carried out by the quasi-stochastic collection equation, which is a whole different thing. But it basically evaluates a more different number of drops you have. It kind of evaluates how many of them would collide, which one would grow in size, which one would not touch each other at all. And the more of them you have, the more of them you have to solve for. Am I?
If I can just chime in here, I would point out that if you have 30 bins, you can have a collision between particles from any bin, right? So essentially you have 900 bin pairs where you have to calculate the rate of collisions and therefore the effect on the tendencies. So there's a lot of possibilities to consider in these models.
Okay. And then the neural network, in comparison to this tau bin scheme, replaces the quasi-stochastic collection, because the quasi-stochastic collection has quadratic runtime if it has to compare every bin with every other bin.
Yes. So now instead of doing all this calculation, you're just getting the tendencies from the mass number directly, which have been trained on the data from this scheme.
Okay. So really, like, the whole thing we're replacing here is the quasi-stochastic collection part.
Yeah, you can say that.
Okay, that's great. Thank you.
Yeah.
I have to admit, there's something I'm really not understanding about this approach, right? If you look at Figure 1, we see the outputs to the emulator are pretty simple, right? They're just, if I'm not missing something, they're just 4 numbers. There's the tendencies for the mass or mass fractions and number counts for rain and cloud, right?
Yes.
But the input includes things like things that aren't available from these moments. Some of them are things like air density, okay, that you get from the model. You know, it's compressible Navier-Stokes. Cloud spectral width, I guess you can also compute from the bulk moments. But cloud distribution slope parameter, how can you compute this? I understand you know it for the initial conditions.
Yes.
But how does it help you if you're doing a long climate simulation? Where does lambda c and lambda r come from?
I'm not sure about this. But I actually assume that they just use the same lambda c and lambda r. But if they are looking at how this is evolving in time and then calculating lambda c and lambda r.
But how could they know it, right? Because the model state is going to be completely different from either the control simulation or the training data, right? After you run it a certain number of time steps.
It will change completely.
I'm sorry?
Yeah, it will change completely. The shape of the distribution will change.
So I'm actually quite confused what's actually going on.
Yeah, I don't have the answer to this actually.
Huh. Well, maybe it's worth digging into if we can figure it out.
Yeah.
Is there supplementary information with this paper? Doesn't look like it.
Mm-hmm.
Strange, huh?
Yeah.
I mean, maybe these are constants that get estimated somewhere. I'm just not seeing it. Okay. What do you make of the fact that they are really looking at climate, as opposed to, so we saw Seifert and Rasp also looking at the Lagrangian formulation and trying to build a bulk moment approximation to that, but there they were really interested in getting the correct timing of things, which doesn't seem to be an issue here. Is it safe to say that here we're working on a climate problem, whereas before they were working on a weather problem?
I mean, I think in this case, definitely they are more focused on looking at how these changes in microphysics, parameterizations play out when you are evaluating the climate. That's one of the things that they actually wanted to see, and they are more interested in looking at the climate instead of the weather as such.
I don't see any results about the timing of rain onset.
They don't have on onset as such. They do have other things on precipitation that I already mentioned. But I guess again, rain onset is something that would be more relevant in numerical weather prediction rather than climate.
That's true. That's certainly true. Okay, do we have any more questions from the chat? Let me check the YouTube as well. I don't think we have any questions there, no?
I have another question.
Sure.
I'm not coming from the weather side. I'm more coming from like a machine learning and numerical methods perspective. So excuse me when I'm lacking here some climate knowledge, but so the parameterization scheme they're using assumes scale separation, as in the neural network we in the end have, we share this across every low resolution cell. Is that correct?
Yeah, right.
Okay. Has there been more holistically, did this model sort of talk about what the implications of the scale separation assumption are, or is there any work that tries to relax the scale separation assumption?
Well, I see what you're getting at. I mean, the thing is, or maybe you want to jump in on this in a second too, Shivani. My impression is that in general, this is a property of how parameterizations for subgrid scale processes are done in climate and weather models, and it's not specific to any machine learning application. You assume that you have certain processes you can't resolve, that you can approximate their effects based on the local values of all the state variables, wind speed, pressure, different kinds of moisture at each location on your grid, and you don't need to look at other locations. But this is just generally how these things are implemented in earth science. Shivani, I mean, do you have something more to say to that, maybe?
No, yeah, I agree. That's just the way that this has been designed. That yeah.
I guess it was just so yeah. I think I understand that that's in general how parameterizations works. I guess I was wondering whether that actually is impacting the downstream quality, and whether sort of these highly nonlinear neural networks could help relax the scale separation assumption.
Do you mean by incorporating information from neighboring grid cells?
Yes. Yeah.
Yeah, it's a very interesting question. As far as I know, no one has really tried this yet. I do think that in fluid dynamics, there are attempts to, so out of the Turi group in Munich, there's some attempts to learn corrective tendencies for low resolution fluid dynamical simulations to make them behave like high resolution ones. And there they use conv nets, and they really do look at not just each individual grid cell. It would be interesting to see if you can do a slightly non-local parameterization for climate and weather models that potentially you could make a big gain. You would have to think, though, about the practicality of actually putting that kind of a thing back into a running climate model or weather model. The way these things are written in Fortran, it's not obvious you can just grab any neighboring cell. In principle, it could be done, but it may be a considerable computational bottleneck. Moving the data around.
That's a very good point. Like the actual practicality of how to deploy such a parameterization. Thank you.
Any more questions? Any more general impressions of this paper? The climatologies we saw what are they, monthly or daily means?
It depends. Usually at least monthly. I don't think there's anything daily. No.
So this is a very interesting question also. I mean, okay, the units are, for example, in that figure you're showing, what is this, figure 10. These are millimeters per day, but they're actually based on 3 hourly precipitation averages for warm rain anywhere on the planet. So you're averaging over the whole planet, huh?
Yes, that's how they're calculating the frequency of warm rain events.
Right, which is a fair thing to do. But I think if we want to talk about capturing extreme rain events, for example, in a way which might be useful for flood prediction or storm prediction, then I think maybe one does want to think about slightly smaller regions, huh?
Yeah, and also if you're talking about extreme events, maybe like what they call here extreme events are not actually extreme, they are just extreme values. Like if you're talking about flood and things like that for extreme events, just a warm rain scenario, emulator trained on warm rain scenario wouldn't be enough.
That's a good point. It's very cool they've shared their code. And they even seem to have shared their modified community atmosphere model code to run this stuff. So this is a nice starting point if someone wants to improve this a bit further.
Yeah, they have shared the Fortran part of it and the machine learning part of it together in their GitHub. Yes.
From a machine learning perspective, I sometimes find it hard to get started.
I'm sorry, Björn, you've cut out for a second. I think there you are.
Yeah, sorry, I got a call right during this moment. Do they share their data sets?
Good question. Let's see. There is a link to Zenodo, but I think they share their code rather than their data.
Yeah, I guess maybe the data might be very large.
It might be. I'm struggling to find details on the data, to be honest.
I don't think it should be that large because the training data is 2 years, 25 hours is the output is every 25 hours. They have something like 1.6 million points, data points.
But each one of those will have different locations in space, right?
Yes, 1.6 million points in total for training.
Oh, that's really not much at all.
Exactly. So that's what I'm saying. They probably can share it on Zenodo.
Yeah. But it does seem, I mean, based on the framework that they've described here, even if you can get great results, on that training data, the real test will be when you take your model and plug it back into their atmospheric simulations. Does it produce the right climates, the right weather, and so on? So this is very tough to test if you don't run the model yourself.
Yeah.
Okay, any other closing thoughts? And thanks again, Shivani. An interesting paper. If anyone has ideas for another thing to present, just drop us an email. If you want to present your own work for 5 minutes, drop us an email, and then we will see you again in 2 weeks. Thanks a lot.
Yeah, thanks so much, Shivani, for presenting, and thanks, David, for organizing.
Thanks for joining.